Okay, hello. Um, my name is Alex Wisco, and this is my COMPS presentation for Amherst College on the TREAP data structure. So first of all, before I get into the little details, what exactly is a TREAP? Um, a TREAP is essentially just a tree data structure that holds both the properties of a binary search tree and a heap. So what exactly do I mean by this? First of all, let's look at a binary search tree. So what is a binary search tree? You insert the values one by one, making the tree structure where smaller values go to the left and the larger values go to the right. So let's look at 25 on the left side of the right subtree. 25 is greater than 20, so we'll go to the right, and it is less than 30, so we'll go to the left, resulting in a new leaf with the value 25. Next is the heap. So there are max heaps, min heaps. Either heap will work for a treap. In my example, I'm going to be using a max heap just for consistency throughout the entire presentation. So the heap property, or a max heap rather, property holds that the value of the parent is greater than or equal to the children. So these are a binary search tree and a heap made from um, comprised of the same values. So issues with the binary search tree, as you can see here, if we have the same values from the previous examples and we add them in sequential order, the results is a horribly balanced tree. Looks more like a linked list than a tree, and this would result in O of n runtimes for basic operations. So what do treaps do to try and solve this? Treaps will add random priority values to the initial values. So we have the priority P, which are generated randomly, and the value V, which are the original values we had in the previous example. So I just slapped a random number generator for each of these values, and this is what I got. So let's do a quick run through of building a treap from the same values that we made with the binary search tree and the max heap. So first we're going to add the value 10 with the priority 4. This is our root. But next we need to add the value 15 with the priority of 9. So the max heap property holds that the higher value must be on the top. So this is no good. So what are we going to do? We're going to rotate the priority of 9 on top of 4 for the max heap property. And also 10 is less than 15. So we're going to need to rotate it in such a way that 15 is that 10 is a left child of 15 and the priority 9 is on top of 4. So let's look at the next one. We want to insert 18 into our treap. 10 is greater than 9, but 18 is greater than 15. So what are we going to do? The same thing. We're going to rotate the values and get this. Next, 3 and 20. 3 is good there and 20 is good there, so we'll leave it. 8 and 25. We see that the priority 8 is a larger value than 3. So we'll rotate it. 20 is less than 25, so it is a left child. 130 looks good there. 635, same thing. 6 is greater than 1, so let's rotate. 30 is less than 35, so it is a left child. So we saw a few of the basic operations, insert, rotate, but now let's get into the more specific details of these operations. So first we have insert. It uses the insert method identical in the binary search tree insert. So basically the larger value goes to the right, the smaller value goes to the left, and you will keep doing this until the node you want to insert is a leaf of the tree, or in code terms, both of its children are null. So the addition here is the rotations. So you want to rotate the higher node on top to maintain the property of the max heap rule. So if the parent's left child's priority is greater than the parent's priority, you're going to rotate to the right. If the parent's right child's priority is greater than the parent's, you're going to rotate to the left. So let's look at an example. Here is the same treap with the same values we've been using. Let's say we want to insert the value, or a node with the value 19 and a priority 5. Using the using the original binary search tree insert from the pseudocode, we are going to move to the right of 18 because 19 is larger, the left of 25, and the left of 20 for the same reason, because it is smaller. But now we see that we have a priority of 5 underneath, a left child of priority 3. So since the left child's priority is greater than the parent's priority, what are we going to do? We're going to rotate to the right. Now we have a priority of 5 above priority 3 and the value 20 as a right child of 19, which maintains both the binary search tree property and the max heap property. So now we have rotating. Rotating is basically just variable assignments or pointer manipulation. And basically you just use temporaries to adjust lengths of nodes to account for the heap property. And it's the same thing for the right rotate. Let's look at an example. So here we have 9 and 15 and 4 and 10. 9 is greater than 4. So since it's the right child, we are going to rotate to the left, giving us this. Now let's look at a right rotate. Let's say we want to add a node with the value 8 and the priority 7. We use the binary search tree insert. So 8 is less than 15. It's also less than 10. Now we have the node with the value 8 as a new leaf on the left subtree. So now we're going to use the rotating to determine that since 7, the node with the priority 7 is a left child, and it is greater than the parent node with a priority of 4, we're going to rotate it to the right, giving us this. Now we get to search. Like insert, actually not like insert. Insert is similar to the binary search tree insert, but search is actually identical. So we'll do a quick run through of that. You basically check the root for the desired value. If it's larger, if the root's value is larger, then you're going to look at the right subtree. And if otherwise, you're going to look in the left subtree. Now, we did a quick run through of search because search is included in delete. So first off, the goal for deleting is rotating the desired node down to a leaf and simply nullifying it, which does the same thing as deleting it. So you use binary search tree search to find the node value, the node with the value you're looking for. If the node is a leaf, you nullify it. If it's not a leaf, you decrease the priority to negative infinity, thus letting you float it down to the bottom or down to a leaf, because as the max heap property states, if a parent's priority is less than its child's, you will do a rotate to bring it down one further step. And in delete, you always want to rotate the higher priority of a node's children to the top to account for the max heap rule. So if the left child's priority is greater than the right child's priority, you want to rotate to the right. Otherwise, you want to rotate to the left. And when you follow this in the while loop, once you get down to the leaf, you simply nullify the node, just like in the base case. So let's do an example for this. We have the same tree. We want to delete the node with the value 8 and the node with the value 25 and the priority of 8. So let's look at its children. Its children have priorities of 5 and 6. The right child has the higher priority, so we're going to rotate to the left, which gives us this. Let's look at the children. 5 and 1. The left child's priority is higher, so we're going to rotate to the right. Now we have 3 and 1. 3 is the left child, and its priority is higher than 1, so we are going to rotate to the right. Lastly, there's 1 child, and it's the right child. So since it's the right child, we're going to rotate to the left. And now that it is a leaf, we can nullify it, deleting the node. And this is the structure we started with, the treap we started with, and this is the treap we finished with. So worst case runtime bounds. So one question is a treap height of O log n always guaranteed? So in the earlier example, I did say that the treap aims to fix the linked list looking tree problem, but unfortunately it cannot guarantee that it'll fix it. Let's take a look at this technically valid treap. We have the values 1, 2, and 3, and priorities of 10, 8, and 4, respectively. If you make a treap out of these values, you'll see that you get the exact same looking linked list. And this is the same problem. You have O of n runtimes, not very efficient, horribly balanced. However, there is a paper by Aragon and Seidel from UC Berkeley, written in 1989, that states that the probability of a tree's height being greater than log n, given the properties of randomization, BST rule, and heap rule, is about 1 in 2.5 billion. In other words, let's say we want to make a treep with 10,000 nodes. It is extremely commonly going to have a height of 100, which is, again, O log n. So then we get to the expected runtime. Since it is so commonly, since the height of a tree is so commonly O log n, n being the number of nodes in the tree, we can have an expected runtime for insert, delete, search, all to be O of h, or according to Aragon and Seidel, O log n. And as I mentioned a little bit earlier, since rotating is just variable declarations or pointer manipulation, depending on the language you're using, it has a constant runtime. So now for some benefits of the treap. They are commonly balanced by nature, not guaranteed, but commonly. And given that, they have efficient expected O log n runtimes for basic operations. Random priorities decrease the likelihood of efficiency degradation, and it is a relatively simple implementation of a tree structure, not too hard to figure out in code in Java, Python, C, whatever. And also one thing that I thought was pretty cool about the treap is that it does not provide any information about the data structure's history. So this is more of a security aspect of the treap. And what I mean by this is the heap property changes the structure of the treap all the time. So leaves rotate into the structure, new nodes come in and out, and the root can change, subtrees can change all the time. And basically this gives no hints or information about what value was added when, which I thought was pretty cool. I don't know about any real world applications, like maybe if some classified information was ever stored in a treap, then that would be cool, but not too sure. And now for costs. So in comparison to AVL trees and red-black trees, treeps are less dependable, more inconsistent. This is because, again, the randomness and the use of probability to try and attempt balance, but not always guaranteeing it. Here are a list of some of my sources, and thank you for watching.